And hopefully this is going to stay working today because I didn't get the class notes from the other day. The video's there, the notes aren't there.
Oh, what the class you posted?
Yeah.
I watched your last semester.
Okay. That works too.
You know, for like a similar lesson.
Yeah.
because I didn't get
Oh, I posted the little bit of notes that I was able to. Okay. All right. So on Tuesday's class, we talked about power series, and we were looking at finding intervals of convergence and radiuses of convergence. We just had a general idea of what a power series was. And a lot of them, like it was really based on, at least the beginning ones, was based on the geometric series. So we're going to start looking at how we can start using the geometric series to actually start building up other representations of other functions, which will then allow us to find how they actually do the estimations of values. So we'll actually be able to look at how to find the integral of something that we wouldn't have found the integral otherwise of. So like that there isn't an actual elementary solution for. How does a computer actually estimate those values? They actually use a series, which we're going to look at today. So this was actually from section 11.2, we started looking at the geometric series. So remember the geometric series was we had the sum of whatever x to the n was equals 1 over 1 minus x. That was the solution for it. So whatever the ratio was, which in this case is x, comes out to be 1 over 1 minus that ratio. That was the summation of whatever my geometric series was. Vaguely remember that? Kind of? Okay. When does the geometric series converge? Yeah, when it's less than 1. So the ratio has to be less than 1 or greater than -1. It's between -1 and 1. That's why it shows it as the absolute value is less than 1. So as long as the absolute value of x is less than 1, this all works. All right. So 1 over 1 minus x equals 1 plus x squared plus x to the third plus whatever it is, which is that summation of there. All right. So in essence, what we did in section 11.2 is we went from here and we found that because I wanted to find out what the value converged to. Okay. Well, now we're going to be able to use this to create that summation, which will then allow us to be able to estimate other functions, okay, that are not easily estimatable or that are not easily solvable, I should say. All right, so let's look at this one first. So we have 1 over 1 plus x squared. And they want to change this to some kind of summation. Okay. What we have currently is 1 over 1 minus x equals the summation of 0 is x to the nth power. We know that. So how can I change this to this? So actually, I'm going to change the x to u. So how can I change 1 plus x squared to 1 minus u? What would the u be? Almost negative x squared, because I want it to be a negative. So if u is x squared, then this now becomes negative x squared to the nth power. This.
You write negative x squared, parentheses, negative x, outside parentheses squared.
No. This is one thing. Because if it was negative x squared, then that's just the same as saying x squared. Because the negative would then be disappeared.
So we want the negative outside.
We want the negative as part of, yes. It's negative x squared. Because in essence, what I'm going to do is this ends up becoming this. Because I want that negative side. So this now is my new summation. We do want to make a couple quick little modifications to it so that it actually is looks the proper formatting, I should say. The first one is we pull out the -1 to the nth power because now that makes it an alternating series. And this one now just becomes x to the 2n. Why does it become x to the 2n? A multiplication. When you have exponent raised to an exponent, you multiply them.
Oh, no.
And then, in essence, the n was just, you're distributing it basically to each piece. So, okay. All right. So does everybody see how I went from here to here? Okay. The next thing we want to look at is what's the interval of convergence for this? So this is a geometric series. Which says the absolute value of, I'm going to use u, keep the u there, is less than 1. In this case, my u was negative x squared, right? So that would change. So I end up getting, what's the absolute value of negative x squared? That's just x squared. It'll never be negative, so I don't have to worry about that. So then I take the square root of both sides. So x is less than, x is less than 1 and greater than -1. So x is between -1 and +1. So my interval of convergence is -1 to 1.
How did you,
So because if you take the square root, you end up getting x is less than plus or minus 1,
oh,
which it can't be less than +1 and less than -1 because that wouldn't make, you wouldn't have any difference. So you, in essence, this ends up being, what ends up happening is because of that, it ends up being the absolute value of x is less than 1 because -1 would, or -1/2 would give you a positive type thing there. So it's one of those weird things when you take the square root of a number, when you have an inequality, it ends up being the intersection of them, not outwards. Does that make sense or no? Okay. So if you look at, because when you're doing anything, you're always finding the actual solution, the equal sign, not the actual less than those things. So we have those two numbers. We know it's not equal to those two numbers. The question is where are we shading? So the only numbers that would work for this, if I plugged in 2, So like if 2, 0, and -2, plug in -2, -2 squared is 4, 4 is not less than 1. So I don't want that section. 0 is less than 1, so this section is what I want, and the same thing over there. So that's why it's between -1 and 1. Okay? All right. That's nice and all, but I'm going to do a couple, we're going to do, I think, one more of these, and then I'll actually show you where they're actually really useful.
So expressing that as a sum of power series, that's when we get to sum of -1 to the n times x to the 2n.
Yep. That's representing this
okay.
as a power series.
And find the interval of convergence. That's the -1.
Yes.
Than x less than 1.
Right. So this only, basically what we're saying is this only works when x is between -1 and 1. So it's like, otherwise this method that we just did won't work. We'd have to do something else. All right, so this one we've got x to the third over x plus 2. And somehow I've got to get this to be looking like something like 1 over 1 minus u.
So is that like base for everything?
Yeah. Because that's the initial statement. It was 1 over 1 minus x, or I'm making it u just so we don't get confused with the x's, is this. That's the geometric series. So if I can take and represent it, something that looks like this, I can then find the actual answer for that problem or be able to estimate it. Okay. So what are we going to do in this problem? So I need to somehow change this to that on the bottom, right? Okay, so let's make a quick little change to help me out here. Let's just make this 2 plus x, just so it's in the same order. All right, how am I going to get that to be a 1? So if I divide by 2, that would be 1 plus x over 2, right? But that also means I divided the top by 2, right? Because otherwise, that doesn't help me.
Okay.
Because if I divide the bottom, I have to divide the top, correct? Okay. All right, so what else am I going to have to do to this one? I need to get it to be 1 minus u. We do the same thing we did here. Remember, I just basically changed that plus into 2 minus signs. Because 2 negative signs equal a positive. So I can change this to 1 minus negative x over 2. So now I have x to the third over 2 times 1 over 1 minus negative x over 2. Yes or no? Okay, so this is like this bunch of just algebra stuff. It's like, how can we rewrite this to make it look like that? All right, so I know this equals that, correct? So in this case, u is negative x over 2. So I can change this to negative x over 2 to the nth power. So I change that to that. I haven't touched the x squared, x to the third over 2 yet. So does everybody see how I did? Oh, sorry, 0, infinity.
Oh, yeah.
There you go.
That was-
Okay. So everybody see I got there to there. I will redo my 0 and infinity there now. All right. Does this have an n in it at all? No. So in terms of the series, it's literally just there. Like that's in essence a constant in terms of the series. That wouldn't be changing at all. So we can just bring it down. But now I kind of want to put everything together. So it's all inside the series. So it's one thing. So we can bring this inside. So I have x to the third over 2 times negative x over 2 to the nth. Okay. Now we got to clean this up. The negative sign negative 1 to the nth power. That just comes out. Now I have x to the third. I have x to the third times x to the n, which becomes what? Yes, because multiplication becomes addition. So I have x to the n plus 3. The 2's are on the bottom. What's the 2 become? N plus 1, because that's n and that's the 1. Now, just so we keep the x's kind of by themselves, when you write this, we want to put the negative 1 to the n over 2n plus 1, and then x to the n plus 3 is separate. Because in essence, when you're going to write this out as a polynomial or in expanded terms, don't do this again. When you write this out as expanded terms, this piece right here, that's your coefficient. Those will be the coefficients in front of your x powers. Okay, so that's why we want to keep the coefficient separate from the actual x term. Okay? Does that make sense? I know you don't understand why you're doing it. I got that part. Can you do it though? If I gave you this, could you actually then create this, come out and do this at the end? Because it's the algebra. Okay. All right. So, no, yes. There you go. You're welcome. All right. One of the things that we actually haven't done very much in chapter 11 is the actual calculus piece of finding differentiation and integration. So what this next theorem states is, if we have our power series, so here's my power series. As long as it is differentiable, which means it's continuous, I can take the derivative of both sides. Okay. So if I took the derivative of fx, I get f prime of x. And the derivative of this, remember, it basically just comes down whatever the powers are, right? So the C1, this is to the first power, so that would disappear. The second power to the 2 comes down, and now that's to the first power. So now you're just using that, the power rule of differentiation. And your summation at the end is the same concept. No, wrong one. If we took the derivative of that, it'd be n minus 1, and the n would come down in front. So we actually can take the derivative of a series. Same thing is true with your integration. It's the opposite of the power rule. So we take the n and we add 1 to it, and we divide by n plus 1. So we can take the same concept and do the integration of a power series. If you don't want to, because there's a lot of stuff there. That's the derivative and the integral of the summation. Because you don't really need all the extra terms in the middle. So we can actually just take the derivative of whatever that is and the integral of whatever that is, and then do the summation. Yeah. You're just doing the derivative of whatever's inside of it. And the integral of whatever's inside of it. You don't have to actually worry about the summation symbol, because you're not doing the integration of the summation, you're doing the integration of the function that's inside of it. All right. Yeah.
How come for the top from integral I as
It
C plus.
it did the integral. This just didn't do the integral. This actually is the integral of the summation. This one didn't do the actual integral. Yeah, it's just this one's saying, so this one's giving you, this is the actual integral of the power series. You add 1 to the exponent, bring the exponent down. What this statement here is saying is that the summation doesn't actually restrict you from doing the derivative or the integral of whatever's inside of it. You can treat n as a exponent, like you would treat 2 or 3 or 4 or whatever it happens to be. So you can do the derivative of whatever functions inside of it instead of worrying about saying, oh, I have this integral of a summation, I don't know how to do it. So this rule is telling us that I can actually just bring the derivative inside of that summation and then do the summation of whatever I got at the end of that, which is what they did here. See how this works in a second. All right, so I've got ln of 1 plus x. What's the derivative of that? Yeah. Remember the derivative of ln of x is 1 over x. So the derivative of ln of 1 plus x is 1 over 1 plus x. So what's the power series for that?
We do the whole, we do
You can, or we can just, what's u going to be?
we turn 1 plus x into
Yeah. Mhm. Okay, which we will then pull the negative 1 out. So that's that. Correct? Okay, but that's not what I wanted. I wanted ln of 1 plus x, right? So if I took the integral of 1 over 1 plus x, does that give me that?
yes.
Yes. Right? Because we did the derivative to get it. The opposite of that would be the integral, right? So if the integral of that gives me that, so ln of 1 plus x equals the integral of 1 over 1 plus x dx.
Do we ever do plus c? Yes.
You can. We're not going to worry about the plus c yet. We're going to find the c in a second. That's why I didn't worry about that in that piece. So I can now do the integral of negative 1 to the n, x to the n dx. Are we to there?
Brain lines or right?
Well, I'm going to hope you wrote it. Brain-wise. Where have I lost you? Other than the
It's not that I'm lost, it's just that I don't know where we're going, so it doesn't make sense to me.
the goal is to get this. I want to figure out what that is as a power series. I want to be able to estimate ln of 1 plus something. Because as of right now, can you tell me what ln, like ln of 1 we can do, right? ln of 1 is 0. Could you tell me what ln of 1.5 is? No. So the goal is we want to be able to figure that out. So you have to remember 99% of math was done pre-calculator and pre-computer. Okay. So when they were originally doing these, they had to have a way to figure these things out and to get the actual answers for them. We no longer do because we have computers. So the question is why am I teaching you this? Haha. Because it's actually really important for you to understand how the computer even does it, depending on what you're looking at going into. A lot of people look to, like in these classes, looking to go into engineering or computers or electronic, like those type of things. And understanding how that stuff works is still actually important. So like when you plug into your calculator and get an answer, the calculator doesn't do ln. The calculator is doing addition and subtraction. It is doing a summation of something. And that's where this comes into play. So the calculator needs to figure out like, okay, I know how to estimate ln of this because this is the summation for ln. For whatever value you're going to give me, it can actually do that for you. So we've got this. I want to do the integral of this. Okay. So if we're doing the integral of that, what do I got to do? All right. Let's take a step back because I don't think you're going to look at it and understand where that's coming from. So let's look at this summation. So this one, let's look at the summation right here, the one that I'm going to do the integral of. Okay, that would give me what? What's the first term? If n is 0, what do I get? No, I get 1. Nope. -1 to the 0 power is 1. X to the 0 power is 1. So I get 1. If I plug in 1, what do I get? Negative x, right? If I plug in 2, what do I get? If I plug in 3, what do I get? Plus x to the 4th, plus, and it just keeps going, right? Yes? Yeah, but it's plus or minus, it doesn't matter. Don't worry. No, you're fine. I literally, so it's like, it's funny. It's funny because I literally had to do that recently in some stuff I was doing. And I put the minus there and I'm like, I don't want the minus there. And then I saw another problem with the pluses and I'm like, oh crap, we kind of need the pluses there. But I don't want to put a minus because it doesn't continue with the minuses. It's always a plus at the end. I had to do a lot of research to figure out if it was always a plus at the end. All right. So what is the integral of this? What's the integral of what? It's x. Actually, let me change the color.
It's the color will help you understand.
Well,
Appreciate the effort.
not necessarily, but at least it's going to like differentiate the notes. Okay, so the integral of 1 is x, right? What's the integral of x? X squared over 2. What's the integral of x squared? What's the integral of x to the 3rd?
We're gonna make you answer all of them.
And then this one is x to the 5th over 5. And it keeps going, right? Good. So if I was going to write that as a summation, what is the summation? So -1 to the n. So what's the first term of that?
So you can't do that.
I couldn't do that, right? All right, let's change this to 1. Because I can do that. Does it now work out correct? So why don't I just do that?
Like that a lot. We do 0 or 1. Is that what we? Oh no.
Yeah. For the first time it works.
Does that give me my terms that I have?
I'm seeing it, yeah. I'm seeing it. I think it works.
So the first term is going to be, this will be 1. End of the 1 over 1 is that. 2 is going to be a negative because that'll be -1 to the first. Okay. So my negatives will go back and forth. That's right. 2 squared over 2, x squared over 3. So yeah. Okay. If I wanted it as the 0, I really just have to shift all these 1, right? So it's going to be -1 to the n, and that'll be x to the n plus 1 over n plus 1, correct?
All right. I'll take it.
Does that give me all my right terms? Because the 0, 1 is going to give me, that'll be positive, and that's x over 1. The first one, that'll be negative. So n1 will be negative, but that'll be n2, x2 over 2. So yeah. All right. So I had, which we originally were trying to find out, was the integral of n equals 0 to infinity of -1 to the n, x to the n. What's the integral of x to the n? N plus 1. X to the n plus 1 divided by n plus 1.
Word? Is this like a, is this a proof? Is that what we just did?
Well, no.
So this is like,
We actually solved the problem that I originally was asking you to. But what I did at the end was I wanted to show you that the integration works the way that you normally would have thought it would have worked. Okay, because originally I was hoping to go from here to here for like this one step.
One step.
Yeah, because I wanted to, I was hoping you would recognize that the integral works, but you didn't. So I'm like, okay, let's take it and actually work through the process. So you're in essence doing the integral of every term. King is the terms go on forever, so you can't do it. So you do the integral of a certain number of terms, you find the pattern. Once you find the pattern, you get the answer. However, what I want you to see is that the integral just, it works. You could just take the integral of x to the n. What's the integral of x to the n? X to the n plus 1 divided by n plus 1. Just like the power rule that you did at the very beginning, the very first integral rule you learned. Okay, that's all you're doing. Which I'm going to teach my Calc 1 class next week.
so this problem is you are given natural log of 1 plus x.
Correct. So what we found, so let me write the actual final answer. The natural log of 1 plus x equals n to the 0 negative 1 to the n over x to the n plus 1, n plus 1.
Times x to the n. What is that?
This,
That's that what equals in terms of the derivative?
yeah, that's the derivative, that's the integral of that we found. But what this equals, this is literally this. This is exactly that. Okay. So if I told you x was 1/2, we could now use this to find the actual answer of ln of 1.5. Am I going to do that? No.
Well, why do we, so the first step is to take the derivative.
So in this one, what we found was we're looking at ln of 1 plus x. And at that point, we don't have anything that would work. Okay. So ln of 1 plus x, we don't have a power series. The only power series we have is the geometric one that we already looked at. That 1 over 1 plus or 1 over 1 minus x equals the summation of x to the n. So the goal was, okay, how could I take this and change it to something that I can do? Okay. And what the book said, and I knew you guys wouldn't have actually recognized this off the top of your head, that's why I asked, is you should recognize that that is the derivative, or is the derivative gives you this. So the derivative of this is this, which, like I said, most of you probably wouldn't have just recognized that off the top of your head. So that's why I asked, what's the derivative of it? And then, okay, once we've got that, and we're like, oh, that's something I can work with.
So it could be the antiderivative.
Right. If I took the antiderivative of that, I get back to here. So by the time I can take the antiderivative of the other side and get back to what the original problem was.
So if we're encountered like these types of problems, step one is to take the derivative.
Not always. Step one is to do something to get to where you need to get to. It's not always going to be take the derivative. It
Oh, so the form that we want to,
is 1 over 1 minus something.
okay,
That's the goal, is to get it to something that looks like that.
this isn't straightforward.
It is not. It is not.
Like a list of things like in a row to check.
This is logic. Okay, it is not always going to be, oh, yep, it's this, you're good. All right. All right. Tangent negative 1 of the arctangent of x. Remember, my goal is to get to look something like that. Because I know that
Take the end of the derivative.
is u to the n. Remember, my goal is to get it to look something like that. What do you mean?
There's a rule where like it's 1 over a minus x, whatever. That it turns into the how do you say that again? Opposite tangent
Arctangent?
or tangent. Yeah. Well, it's low right now, but yeah, I remember that.
You're close.
What do you mean close?
You're close.
It's like 1 over x minus a squared something.
So the integral of, it's what was it? Yeah. Oh, sorry, actually, I wrote that backwards. The integral of that is tangent of negative x.
You're taking the derivative.
Okay. All right. How do I get that to look like that?
Substitution.
What was the very first problem I did today?
Um,
X plus two, no. No, it's one plus x squared.
Yeah.
So u equals negative x squared.
So what was the summation? What was the answer? We already did this.
Negative one, the n times x to the 2n.
Right. So that's that. Correct? We did that at the beginning. There was a reason we did that one first. All right. So I want to take the integral of that. Oh, I forgot the summation symbol. So what's the integral of that? What's the integral of negative 1 to the n? Negative 1 to the n. It's constant, so it's out in front anyway. What's the integral of x to the 2n? So that's what direct tangent of x equals.
That's great.
I feel it's 3.
Some people think say so. I've heard a lot of people say Calc 2 is the hardest one. Yeah. Calc 3 is multidimensional. You're looking at multivariable, 3 dimensions, stuff like that. So it really just depends on how well your brain works with 3 dimensions.
Hopefully better than that.
When we take the
The
integral-
algebra is not going away though.
So when we take the integral, it's like summation of whatever dx. Is that-
Yeah.
Would it ever be like dn?
Because you're taking the integral based on x, because my original problem over here was an x. That's why the n is literally being treated as a number and not a variable. Otherwise, this would look way messier.
N is a variable.
Yeah, no, and so n in terms of the summation, n is not. N is a bunch of numbers that I'm plugging in. That's why when we looked here, we did this problem over here. In essence, you can look at the integration of every single term as you go through, because that's what the summation really is. So if you're taking the integration of every term, those n's don't exist. They're numbers. And that's why you can think about it as not a variable, because it's something that the summation's telling you exactly what number you're plugging in at all of those times. A variable, you can plug in technically anything, where the n you can't. Subtle difference. All right. I want to see something real quick. Give me 1 second. All right. I'm going to do something because I want to show you something very cool. Not that you might think it's cool, but it is kind of cool. Not that one. All right. If X is 1, so we're going to say X equals 1. What's the first term? So we're doing, so in essence, I'm doing and if that's 1, the whole top is always going to be 1, right? Because 1 raised to any power is 1. So 1 over 2n plus 1. Okay. What's the first term? What's the second term?
-2.
Yeah.
-1/3.
Plug in 1, the n. And what do you get? I actually do get a -1/3 in this case. You got it right the second time, sorry.
Yes.
What's the next one?
+4/3.
Nope. We're plugging plug in 2, you get 1 over 5. And then 1 over 7. And 1 over 9. And 1 over 11. And it just keeps going, right?
You do series and Desmos.
So I don't think you can do it in the, you have to do it in the graphing calculator. So, but there was a reason I wanted you to do this. So we have 1 minus 1 over 3 plus 1 over 5 minus 1 over 7 plus 1 over 9 minus 1 over 11 plus 1 over 13
I want you to type it out for you. Give you the same.
minus 1 over 15. Well, it just keeps going, right? It's just going to keep going, getting closer and closer to the actual value, right?
Yeah.
Okay. Now, in Desmos, if you look at the graphing calculator, we're doing
Just type in 6.
now sum. If you type in summation, it gives you that. So we're doing from 0 to, we'll just do a whole bunch of numbers. You can change that top. You can't put infinity, but you can type any number you want in there. So -1 for the n. And then it was 1 over 1 over 2n plus 1. And if you keep adding zeros up there, it really doesn't get much closer to than that, right? Okay. That might not look like anything really cool. But if I do 4 times it, what's that?
Like 5.
That's pi.
What are we doing?
We took the series that we just did. We took this series.
You're saying one of the.
And I plugged in x as 1. Okay. What's the arctangent of 1?
32/6.
Nope.
33/6.
First of all, arctangent's giving me the angle, not the answer. So arctangent of 1 is pi over 4.
Uh,
So this summation that we just came up with here okay, will give me the answer of pi over 4. So if I multiply by 4, I get pi. So this summation right here will calculate pi.
Why x equals 1?
Because that's arctangent of 1 is pi over 4. Because arctangent tells you what the value of tangent is going to give you 1, which is pi over 4. So this series, by multiplying it by 4, it ends up giving you pi over 4, but if you multiply by 4, will give you pi. And it will calculate it out to as many decimal places as you'd like to. So if you ever ask your computer to give you pi, and actually they use this as a benchmarking tool to see how fast your computer can run, like if you see how fast the processor runs, they use it to calculate pi because they have an exact number of like, okay, this is how long it should take it to calculate pi because it literally has to do this summation that many times.
It doesn't do it an infinite number.
No, it's going to do it. So it depends on how, so you can use it to determine how fast your computer is going to do the calculations. If you say you want pi to the 1 billionth place, and it will actually add up enough digits to get to that place. So, but in essence, we just found the series for it. Huh? Yeah. But again, you got to remember, this stuff was done pre-computer, pre-calculator. So being able to calculate, like, we've been trying to calculate pi out for thousands of years. Like, the Greeks figured out pi was about 3. And then they got it to, after the Greeks, because the Greeks did not like decimal places, they got it to 3.1 and then the 3.4, and they got it closer and closer and closer. When they started looking at calculus, so when Newton invented calculus and Leibniz invented calculus, they then started figuring out ways to be able to use that to estimate pi to even more decimal places. And this summation will actually find pi to an infinite number of decimal places. I think the record right now, somebody knows pi to like 80-something thousand decimal places. Can recite it. That's like the Guinness Book of World Records. It's ridiculous. I have no clue. I'm a math person, and I have no clue why you would want to do that. It's the stupid bragging rights of people. All right, so that's really where like these summations and stuff can really come into play. It's like we can use it to calculate really complex things that we wouldn't be able to calculate otherwise.
I probably have nothing else. Had just numbers.
Oh, that guy, I don't know.
So the previous problem, we had ln of 1 plus x. The first step there was to give the
We did the derivative.
We take the derivative
Yeah.
because that put us in a form close to
Yes.
1 over 1 plus or 1 over 1 minus something.
Yes, and this one we actually did a very similar thing.
And in this one, the integral.
Actually, we took the derivative. The derivative of that tangent of negative 1 of x is 1 over 1 plus x squared.
Oh, because the integral of that
Is the tangent, right. So we actually also did the derivative.
So taking the derivative, that's one method.
That's one method. You also could technically do the integral. You could do the integral of it as well to go backwards. So either one is actually a possibility. All right. Let's look at this one. So first step, before we even do the problem. Can you do that integral?
Sir.
You do use substitution, that gives you x to the 6 left over.
Right, and I don't have an x to the 6th.
Part that thing out.
Can you? Can't do U substitution.
Yeah.
X to the 6th dx, but I don't have an x to the 6th.
I just put it one. I just be like that, and then I just put the VES one.
Oh, you're doing integration, integration by parts, which you can't do that either. Because integration by parts, first of all, has to be multiplication, not division.
Can you use division?
Nope. Partial fractions is the division part, but then we have to somehow break up the 1 plus x to the 7th, which you can't do either. And just to show you, if you do Symbol Lab, it literally tells you they can't do it. Okay. So there is situations where there's going to be intervals you can't do. But we still need an answer. We still want to be able to find an answer to it. So the question is okay, if we can't do it, what other methods can we have? And one of those methods is the series that we were just doing. So this right here looks like that kind of format that I want, right? The 1 over 1 minus x or 1 over 1 minus u, depending on how you want to think about it. So if we look at just that piece, and I want to write that as a summation, how would I do that as a summation? What's u going to be? Okay.
So like the previous one, x squared became x squared became x to n. Would x to the 7th become x 7n?
Yeah.
I guessed. Right.
Yeah. Now, do you want to see why?
Well,
What's u? What's u going to be? Negative x to the 7th, right? And remember, that's u to the n is going to be over there. So that's negative x to the 7th n, which is negative 1 to the n, x to the 7n. All right. But we wanted the integral of this, right? So I really want the integral of this side. So the integral of 1 over 1 plus x to the 7th. What is the integral of that summation? What's the integral of negative 1 to the n? This negative 1 to the n. It's the integral of x to the 7n. Yep. So that's the integral.
The summation notation, that just carries over.
Yeah. Because you're in essence, again, the integral is actually inside. So when you're doing the integral of it, you're doing the integral. You're not doing the integral of the summation. You're actually doing the integral of the inside piece. That was what this said right here. The integral of the summation thing, you're just doing the summation of that integral. So we don't have to actually do the integral piece of the summation. We're just doing the integral of that thing inside of it.
Now, this was easy because we just had a 1 plus some.
Correct.
In previous question, Didn't we have like a two
We
plus
had-
something and we had to divide?
Yes, we had to divide by 2. You always want to get it to 1. We actually always want to get it to 1 minus something. but-
Okay,
yeah. That's, you always want to get it to 1 over 1 minus something. That's the goal, always. All right. So the second part of this problem,
So we just plug in numbers, so we get to, like the 7th decimal point.
well, they wanted this from 0 to 0.5, right? And we know that this is -1 to the n, x to the 7n plus 1 over 7n plus 1. All right, so we know what that is that. Evaluated at x is 0 and x is 0.5.
The one, dot,
So
it's not. That is 0.
if x is 0, this whole thing's gone, right? So I don't even have to worry about the 0. Actually, I'm going to change this to 1.1 over 2. Okay, so we're really just worried about the x as a half. So, because it's going to be nicer to deal with the fraction than actually deal with the decimal. So my first term is what? So we're doing n equals 0 to infinity of -1 over n, 1/2. What? This is 7n plus 1 over 7n plus 1. So my first term is what? This is going to be messy, right? With the half? Okay. So let's not make it messy. Oh, that's not what I wanted to do. That's what I wanted to do. All right, let's not make this messy. What's the first term of my original series?
0.
There's just 1, right? Oh, no, it's not just 1. That's positive. If I plug in 0 to there, I get x, and that's just 1, right? So this first term is just x.
I thought the first term is 0.
No, if we're looking at this,
Maybe the first term.
if we're looking at this, okay, if I plug in x as 0, what do I get? I'm sorry, not if I plug in n as 0, what do I get?
It's
Just x, right? Because that's 1, and that's x to the first and over 1.
Wait, X. Yeah.
Okay, if I plug in n as 1, what do I get?
Where?
No,
Over 2.
no.
Damn. Over 14. Over 8.
Aiden, shut up. You're right. It is over 8. Very good. What's the top then? It's also 8. What's the next term? Yeah. What's the next term?
2.
And we'll go one more term.
29.
And x is going to be what? 1/2, right? So make x 1/2. Okay. So you got how I got that?
Yeah.
Okay. So now
It's like Inception.
the goal was to figure out what, if I plug in 0 to that, it's 0. So I don't have to worry about the 0 term. I have to plug in the 1/2 now. I am not doing this out by hand. We're going to use a calculator for this.
How many to the n terms do you go to?
They wanted it to within x to or 10 to the negative 7th power. They wanted it to within 7 decimal places is the question they wanted.
If you keep adding n terms to the you get more decimal
Yeah.
places?
So let's look at this. So
Yeah.
if I plugged in 1/2 to the 29th power over 29. So 1/2 to the 29th power over 29.
I get to the
Negative 11th power.
so we went past what
So we don't even, that's farther than we need.
okay.
If I change it to 22, that's the 8th power. That's probably as far as we're going to need to go. So it was 1 minus. Oh, shoot. Oh, there we go. Let's see. What was it? 7 was the first one? Oh, 8. That's right. Over 8. And then plus. It was 15, right? Over 15. And then minus that.
Shouldn't the first term be 1/2?
Hold on. Oh, you're right. You're right. Because it was just X. So there is the answer to 1, 2, 3, 4, 5, 6, 7 places. And if I was to add in the other one, hold on, leave that there. Plus 1/2 to the 29th divided by 29. It does not change my 7th place. It doesn't even change my 8th or my 9th place. So you're asking like how many places do we have to go? In this case, we only had to go 4 ends to get the actual answer. So you can see how we used a series to approximate an integral that we couldn't do.
The name of this series is the power series.
Yes. These are applications of the power series. All right.
For these, the solutions for these types of problems, are we ever going to need to find like an interval of convergence or anything like
So
that? Or a radius?
so these are all based on the geometric series, right? What was the very first term I started with? The very first problem I started with was
1 over 1 plus x squared.
no, the rule was 1 over 1 minus x, right, equals the summation of x to the nth power. The very, very first slide.
Summation of,
We're not going to do this. I want to show you this. Okay, cool. I'll show you this because that let me answer your question. This one. This right here, that's the geometric series. Geometric series is always going to be the same. Since we're basing it on the geometric series, these are all going to be the same.
oh, that's why. So all of our answers were the closest one.
That's why we only plugged in numbers that were less than 1. So in this one, I plugged in 0 and 0.5. All right, here's one like real life application of this. So this is known as a basal function. So this is actually if you play the drums, the entire sound comes from the vibration of the drum head. That is a representation of the model of the drum head, the actual vibration. And this is the basal function. We are not doing this.
You write it down,
No, you don't have to.
you're gonna slide it on the test.
No. So it was a function that they were then able to identify as a series to be able to estimate values. So it works for all values, because notice this is not totally the geometric series. It has the geometric series in there. It's got the x to the 2n, but there's other stuff in there as well. All the rest of the stuff is basically going to be your coefficients. And that's going to be your powers. So, but it does allow us to actually model vibrations of sound, which when he figured this out was really cool. So, all right, I think we're done for the night. So I wanted to get into some things where we're actually looking at why we're doing the series, because it is different than the rest of calculus. It's not a formulaic thing. You just do this, do this, do this. You got that, you get the answer. It is a lot of thought process put into it and a lot of logic that has to go into it. But it really does give us the ability to do stuff that we wouldn't otherwise be able to do. It gives us that ability to approximate values that we couldn't actually do otherwise in a lot easier way than some of the other methods that are out there.
Is there a problem associated with,
Basals? No. This?
so like,
There was. I'm not doing it. I just wanted to show
how would
you.
we get rid of the factorial?
So this,
Yeah,
the question for this one was, they wanted you to find the domain and the derivative of it. They didn't want you to actually solve it. But we can actually use it to plug in values for. So this is what they actually do with it. You're not actually getting rid of the factorial. Factorial is part of the problem. So this is the partial sums of it. So if you look at the very first term, so like the fourth term, like the first 4 or 5 terms actually, is this. You don't get rid of the x factorial. You're leaving it there. You're just using that. And now we can plug in any value for x we want to be able to estimate or approximate the vibration on that.
It's in the Bessel functions.
Yep.
X represents seconds.
I don't know. I don't know actually. I don't know.
Force, or like, and n is seconds, right?
No, I don't know the answer to that.
Oh,
I will honestly tell you, I don't know the answer to it. I will hold on, give me a second.
That's one thing that's
Google
really
trees.
tripping me up about these problems is that there's the M and then there's the X. And I'm just not sure.
Okay, so the X is your variable.
Yeah,
So that is going to be whatever we normally would have been calculating. So like in the easiest one to look at so that we actually know what it's talking about is the one we did with this. The tangent, the
Yes.
arctangent of
I'm
X.
looking at that right now.
So the X is going to be the answer of whatever the tangent function would give me. Okay. So when we're looking at this, that's the same concept. So in the example that we did, I plugged in, I said X was 1.
Oh, so the N just gives us how accurate.
Yeah, the N is your summation. That is literally how far else you want to go. You can literally go to infinity if you want to get as accurate as you can. You don't have to. And that's why when we did this problem, we figured out that we actually only had to go 4 places, 4 N's. And it gave me my accuracy within 7 decimal places. Okay. So the N is whatever representing whatever, or the X is representing whatever thing we're talking about. And the Basel function, I honestly don't know because I've never really used it. It's more of a physics and thing that I just didn't do it. But the N is not your variable. That's why we don't have to worry about integrating the N. The N is how many terms I need to go out to get to whatever accuracy I want. Okay. All right. Your test is still not next week. Your test is going to be the 25th, so don't worry about that.
20th,
25th.
25th.
So we're going to do the Taylor series next week, which is more applications of your series. So. All right, stop recording.